Okay, so now we're going to look into the basic of food analysis, which is proximate analysis of food. In this session, I'm going to focus more on the analysis of moisture and ash. Okay, so for this topic, I'm just going to give an overview of different approaches that you can take in analyzing different food composition. Particularly, we're focusing on the proximate. Okay, water, ash and minerals. Okay, fat, protein, fibers, and carbohydrates. Knowing the composition of food is important. Okay, how are we going to get information from this? We can calculate from the recipe of the cooked food, provided that we have information on the raw ingredients. Unfortunately, there are many factors that may influence the composition of the raw ingredients. So, most cases we have covered on how we can do sampling plan. Okay, on how we do the sample preparation. Okay, prior to that, we need to select the analytical methods based on our objective of the study. So here, when it comes to food analysis, it can either be proximate. This is the gross estimate of the major components and minor components of food. You can also go for minerals, looking into fat-soluble vitamins, water-soluble vitamins, amino acids. We can look at protein composition as well as the fatty acids and cholesterol. So all this will contribute to high quality analytical data that will allow us to establish the database of food composition. So what is proximate analysis? It is a general analysis that will give us a crude approximation of the food composition, and these are done to satisfy label requirements. There are many ways of how there are many choices on how you're going to measure components that need to be included in the label. But when it comes to proximate, it's important to use standard methods. So here we have a food packaging, and we can see that at the back of this food packaging there's a nutrition fact. Okay, so this food label, what's the purpose of having it in the packaging is to for the producer to inform consumers about the nutritional value, what are the food composition in the food product, and for them to make sure that the product meets standards, okay, and also following the guidelines. So from this, if you observe this food label, you may recognize there are several food components that are commonly listed. So how do we determine the composition of food and what are needed to be labeled in the food label? Okay, the standard methods that we use for this purpose is to use proximate analysis. This is where 100% of the food product is made up of the sum of percentage of moisture, ash, fat, protein, as well as total carbohydrate. But what's interesting to observe here is that if you look at the list of these nutrition that are listed in the food label, there are two components in the proximate that is not reported, is not listed, okay, which is moisture and ash. Now the question comes, why do we have to measure moisture and ash if they are not listed in the food label? The proximate analysis is following an established official methods, okay, although they are not properly listed on the label, but we know that for this different components of food, there are different official methods being used. For example, moisture, okay, the official methods that are commonly used will be oven drying methods. For ash, this is dry ashing methods. For fat, okay, I'm going to elaborate more on this later, but for crude fat is Soxhlet and Mojonia. For crude proteins, we can use Keldal and Dumas, whereas for the total carbohydrate, Okay, are there any specific methods? Unfortunately, we don't have any specific methods. Okay, so because of that, in proximate analysis, to determine total carbohydrate, what you have to do is to calculate the difference, because we can, in proximate analysis, we can measure the percentage of moisture, ash, fat, and protein. So what you can do is to add up all these percentage of these different components, and then you deduct 100 to these sum values. Okay, the reason why for carbohydrates we have to use this calculation is because currently there's no methods that is able to measure total carbohydrate. This is because of the diversity of the carbohydrate components. We have dietary fibers, starch, sugars with different composition, and there's no, as I mentioned, there's no specific methods that will accurately measure each of these components. So even if you try to use different methods, if you add up, you are not going to get 100%. So that's why we use the difference method. Later we're going to look at how there are different methods available for this food analysis. However, for Proximate, despite the availability of these rapid methods, you must use approved or official methods. The reason why is this official method has been tested across labs and products. They have undergone this proficiency testing. So the data that being produced by utilizing these methods is highly reliable. Okay, example for Proximate, we use AOAC methods. Okay, so for Proximate moisture, we use oven drying methods. For ash, we use dry ashing methods. For fat, although people mistakenly thought that it's sufficient to perform crude fat analysis by performing Soxhlet or Montagnier, but if you look back into the food labeling, okay, you also have to report on the saturated and non-saturated fat. This is not, you're not going to be able to get this data by performing crude fat analysis. Okay. For proteins, we can perform, we can measure the crude protein content in food. Normally, the methods that we use here, this Cadal and Dumas, is based on the nitrogen content, because if you look at the composition, the elemental composition of most of the major component of food, proteins are the only components that contain nitrogen in its chemical composition. Okay, so we use that as an indication of the protein content. Okay, and then lastly, on the total carbohydrate is by calculating differences. So when it comes to fat content, although we can determine total crude fat content by Soxhlet and Montagnier methods, but you still have to perform GC, gas chromatography analysis of fatty acids, okay, in order for you to determine the total fat and saturated fat. So by performing this GC analysis, you'll be able to determine the fatty acid composition. So what you need to do is to total up this triglyceride, okay, and this will give you values, okay, concentration or the percentage of your saturated and total fat. Let's move on to moisture analysis. So what is moisture analysis? This is an analysis to determine water, which is moisture content, and also water activity of food to provide a complete moisture analysis. Okay, we are talking about adsorbed water as well as free water here. Okay, chemically bound water unfortunately are not going to be measured using this moisture analysis. It's important for us to differentiate between water content and water activity. They are not supposed to be used interchangeably because they both mean different. They both have different meaning. For water or moisture content, this is the total quantity of water. We talk about free water and salt water, but it doesn't include any chemically bound water that is contained in a food or other material. So what happens after we remove water, the dry matter that's left, we call this as total solid. We express the composition of total solid as dry matter. Water activity, on the other hand, is the relationship between the partial vapor pressure of water in the atmosphere above the sample and the vapor pressure of pure water at the same temperature. Normally, we express this as a range from 0 to 1. There's no specific unit to water activity. Okay, so we can also calculate water activity by dividing the equilibrium relative humidity with 100. So you may wonder why is it important to perform moisture analysis of the food. This is important because it will indicate preservation and stability, especially if you are studying on shelf life. Okay, it's also a quality, one of the quality factor is to look into the moisture analysis. Okay, in some cases, for the sake of convenience in packaging or shipping, your food product may need to be diluted or concentrated. Okay, so to determine that, you need to perform moisture analysis. It's also important so that by measuring moisture, you'll be able to know whether your product meet the compositional standards and standards of identity. We also need to perform moisture analysis for the proximate analysis. Okay, this is required for the nutritional labeling. Okay, for the nutritional label calculation. And lastly is for you to express result of other analytical determination on dry weight basis. This is for comparison. There are many methods that we can use to analyze moisture, but in general we can further divide them into 4 types. Okay, the most commonly used methods is where we physically remove the water. Okay, so here in this diagram here, you can see the one that is circled in orange are the official methods, okay, for moisture analysis. Okay, so 2 of them falls under this physical removal of water methods. Okay, most commonly used method will be the hot air oven, where you heat food product up to 105 to 110 degrees Celsius. There's also another method such as vacuum oven with lower temperature. Also have freeze drying, microwave oven, and din and start distillation. Okay, for chemical reactivity, we have here Carl Fisher. I will explain in more detail later on, and we also have physical methods and chromatography. But both of these methods are expensive. Okay, both of these methods are expensive and they can be highly accurate but not suitable for regular analysis or for routine analysis of moisture content. Here just to show you a summary of different methods by physical removal of water. We have here, as I mentioned, the most commonly used methods, which is a forced draft oven. Okay, this is part of the official methods. Okay, so these methods is highly versatile. It can be used, can be applied to most of food, the majority of food, except for food that is rich in sugar and fat. The reason why is because if food is high in sugar and fat, it may induce Maillard reactions, because you have to remember this sample will be heated up to more than 100 degrees Celsius. Okay, so these are the limitations. It will lead to also the caramelization of sugar, degradation of unsaturated fats, and loss of other volatiles. So by doing so, if you're forced to use these techniques or these methods on this sugar-rich or fat-rich product, you are going to either overestimate or underestimate the moisture content. But these methods is considerably cheap. Okay, so we also have here vacuum oven. Okay, it requires less temperature compared to the hot air oven. Okay, so this can be applied to most food, but the problem is because despite having lower temperature, it's still sufficient to cause loss of volatile compound. Okay, again, cost-wise, this is considerably cheap. We also have a microwave oven that is suitable for medium or high moisture product. Okay, the only side effect of this is that the product can become charred. Okay, and what I didn't explain in detail here will be the freeze drying. Freeze drying is more expensive compared to these three methods because you perform it under vacuum condition and low temperature to remove the moisture content. But if you are interested in analyzing, for example, antioxidant or any component that is very heat sensitive, for example, you want to look into metabolites or even proteins, okay, you may want to opt for these freeze drying methods. For food that is high in volatile compound, you may want to use distillation techniques. Okay, but the problem with distillation techniques, you may use hazardous solvent, so this will be one of the limitation. But in terms of its cost, it is relatively cheap. But because there are more accurate methods that we can use to determine moisture content, so this particular methods is becoming rare. Okay, it's rarely being used in current situation. For oven drying methods, there are ways of how you can calculate the percentage of moisture content. This is the simplest technique where we weigh the sample after being dried, okay, because any weight loss is equivalent to moisture content. Okay, what you can either calculate the moisture based on wet basis or dry basis. But again, there are a few things that you need to consider when you are performing moisture analysis using oven drying methods. One is to aware that some food constituent may be decomposed, such as by inducing Maillard reactions, okay, or the loss of volatiles, or some of the water may be consumed during the reaction. This may lead in overestimation or underestimation of the moisture content. Okay. When you perform oven drying, you also want to control the temperature. Have to make sure that they must be consistent so that they dry up to the constant weight. Okay, and then for samples that is easily splattered and also to reduce airflow, you may want to use cover. Okay, and then lastly, it's also important to prevent surface crust formation, because if this happens, it makes evaporation difficult. Your sample become into chunks. So this will prevent the drying process. So what's going to happen is that you are going to underestimate the actual moisture content. Okay, the second type of method that we can use to analyze moisture is by chemical reactivity. So there's this one method that is also is also an official method to analyze moisture, which is Carl Fisher. So this method is suitable to be used to analyze moisture content in low moisture food, okay, such as sweets, okay, we talk about candies here, or dried fruits, as well as for the hygroscopic methods. So good thing about this Carl Fisher method is that the analysis is a rapid analysis. However, you can only analyze one sample at a time, but it is highly accurate and it's the best method to measure low moisture and low fat food. And another good thing is that it doesn't involve any heating. And the cost to run this analysis is considerably cheap. Okay, so in order for you to run this Carl Fisher analysis, you have to perform standardization. where the Karl-Fischer reagent must be titrated with a standard in order to determine the Karl-Fischer reagent water moisture equivalence. Okay, this is to know how much water reacts with 1 ml of the Karl-Fischer reagent. So for the standardization, it can be done by using either pure water, water in methanol, or the most commonly used solvent is the sodium, or solution is the sodium tartrate dehydrate. Okay, we also have these other methods that we can use to analyze moisture content. It falls under physical and chromatography methods, as I mentioned before. These techniques or these methods are expensive because it uses this high throughput instrument. Okay, so for example, for physical methods, we can use nuclear magnetic resonance or NMR, as well as this near infrared spectroscopy. Okay, but then again, in order to use these methods, you need to calibrate with a specific food, and it requires extensive calibration with specific food for the near infrared techniques. However, these are also very dependent on the particle size. For chromatography, we can use gas liquid chromatography or gas solid chromatography, and it's suitable to measure moisture in meat and meat product, but again, it is expensive. There are expensive methods. Other than moisture content, we can also measure water activity. So what is water activity? These are the amount of free water in sample that is not bound and therefore free for microbial growth, for enzymes and vitamin decomposition. And this can then lead to reduced color, taste and flavor stability. Although water activity is not required to be put in the food label, however, it is very important to determine water activity of food because this water activity can affect important quality and safety factors. For example, it indicates whether the water activity can indicate whether the food may be favorable for growth of spoilage and pathogenic microorganisms, and also it will tell the impact rates of chemical reaction. Table just to show you an overall or a general water activity and at what specific range is favorable for the microorganisms to flourish. Okay, if you look at bacteria, it can flourish from 0.94 up to 1. Okay, so most of the food, okay, such as meat, fish, sausage, milk, and cheese, they have high water activity. Okay, at lower water activity, around 9 to 8, 0.9 to 0.87, this range is no longer favorable for the growth of bacteria, but yeast can still survive. Example of product with this level of water activity include salami, okay, dry cheese and margarine. Lower than that, lower than 0.67, okay, up to 0.8, yeast no longer grow in this range, but mold can still survive. Okay, example of food that has water activity around this range include syrup, flour, fruit cake, honey and jellies. Normally at very low water activity, in this particular case, for example, 0.2 to 0.3, is no microorganisms can proliferate. Okay, example for this type of food with this water activity range include cookies, crackers, bread crust, sugar. Okay, that's why you may wonder why for the dried food they tend to have longer shelf life compared to wet food. Okay, these are one of the reasons. Okay, water activity can be measured. Here I'm just going to show you there are two different types of sensor. One is the capacitance sensor and the other one is chilled mirror dew point. So these are one of the common methods used to measure water activity. So if you look at this chilled mirror dew point, okay, you have here a chamber, a sealed chamber where you put your sample, okay, your food sample that is sealed, and it contains a fan. Okay, I'm just going to show you the fan here. Okay, that its function is to circulate air in the headspace, and near to this fan you have infrared thermometer that is able to measure sample temperature. Okay, we also have temperature controlled mirror and a sensor to detect condensation on the mirror. So the mirror temperature is controlled by the thermoelectric Peltier cooler. You can see on top of this chilled mirror, and a photo detector monitor. Okay, that monitors, this photo detector that monitors the reflectance of light of the mirror. Okay, so the water activity of the sample is the same as the relative humidity of the headspace at equilibrium. Okay, it is the headspace relative humidity that is analyzed. So the temperature of the mirror is cooled until condensation from the headspace first appears, which is determined by a change in the reflectance. So when there's a condensation, okay, the temperature of the sample and the mirror are recorded. So temperature of the sample is used to determine the water vapor pressure, okay, which is PO. So this is a pure water vapor pressure, and the dew point temperature is used to determine the vapor pressure of water in the headspace. Okay, so you can then calculate the water activity of the sample by applying equation where water activity equals to the vapor pressure of water in the headspace divided by the vapor pressure of pure water. Okay, so volatiles that may condense on the mirror, such as alcohol, acetic acid, or propylene glycol, may interfere with accurate water activity measurement. Okay, so those are the things that you need to also take into consideration. But not least is that you can also measure moisture sorption isotherm. So what is moisture sorption isotherm? It's a plot of equilibrium relationship between a sample's moisture content and water activity at a constant temperature and pressure. We can use this moisture sorption isotherm to provide hygroscopic information or to know the water holding capacity of the food. Okay, then you can also predict how a sample might respond to different environment. We can use this moisture sorption isotherm data to indicate stability of the food against microbial, physical, and chemical stress. Okay, it tells you, gives you information about the monolayer. Right, next is we're going to look at how we can analyze ash. Next, we're going to look at ash analysis. First thing first, we need to understand what is ash. Okay, ever wonder when you burn food or any component, if you burn them, if you incinerate this material, okay, what's left will be ash. Okay, so this ash is actually inorganic residues from the incineration or oxidation of organic matters in food, which also equal to the total mineral content. Okay, there are three different major types of ashing. Okay, you can go for dry ashing. This is the standard methods used, and this is also the official methods for ash analysis. Okay, so it's suitable for the majority of sample. We also have fat ashing, which is useful for food that is high in fat, and we can use this technique for to prepare for sample prep if we want to perform elemental analysis. We also have this low temperature plasma dry ashing, which is suitable if we want to analyze volatile elemental component. Okay. So ashing is the first step in specific mineral analysis. It can also use as indicator of quality for some product. So dry ashing, which is one of the official method for ash analysis, how we can perform this is by using muffle furnace that is capable of maintaining temperature up to 600 degrees Celsius. So at this temperature, what happens is the water and other volatile materials are vaporized, and all the organic matters are going to be burned in the presence of oxygen in the air into carbon dioxide. Okay, so most minerals are converted to oxides, sulfates, phosphates, and silicates. To perform morphophoresis, you can use different types of crucible. In our faculty, we use the common porcelain crucible, okay, where we place our samples and we put them in this furnace. There are, of course, advantages and disadvantages of using this dry ashing. These are safe methods. In this particular technique, you don't have to perform blank subtraction, and you can analyze multiple samples simultaneously, and this ash can then be further analyzed for specific mineral content. But the problem with this dry ashing is that it takes a long time and requires this expensive equipment, and most of the volatile elements are at risk of being lost, okay, such as zinc, okay, nickel, mercury, and so on and so forth. For wet ashing, what it means is that you oxidize the organic substance by using acid and oxidizing agent, or we can use combination of both acid and oxidizing agent. So example of oxidizing agent used in wet ashing is nitric, perchloric, or sulfuric. Okay, in this technique, minerals are solubilized without volatilization. Okay, so we call this as wet digestion and wet oxidation. In some cases later, if you want to analyze the elements, okay, this mineral composition by using atomic absorption spectroscopy, prior to that analysis, you need to prepare the sample by performing this wet ashing. The good thing about wet ashing is that it only requires low temperature, so mineral will usually stay in solution, and the apparatus required for this wet ashing is simple and oxidation is rapid. But the problem is that this procedure requires a large amount of corrosive reagents. Special perchloric acid hood are required in order to wash down capacity to protect from explosion, and this methods is labor intensive. For low temperature plasma ashing, this is a special type of dry ashing where food are oxidized in partial vacuum by nascent oxygen that is formed by an electromagnetic field. Good thing about this low temperature plasma ashing is that there are less chances of losing trace element by volatilization, but the problem is that it can only feed small number of samples, and this equipment is expensive. Also, other methods that can be used for ash measurements, but this is less utilized, such as soluble insoluble ash in water, ash insoluble in acid, and alkalinity of ash. So taking into consideration of the property of the food matrix, you may want to modify your ashing procedures. For example, if your product is liquid, in liquid form, you may need to pre-dry your sample in order to prevent any spillage. Okay. For spattering product, you may want to use lid or place glass wool over the sample. For protein-rich food, you may need to ash very slowly to ensure complete combustion. This may require more than 24 hours. For high salt, you have to be careful not to heat them at high temperature so that the sodium chloride is not going to be volatilized. For carbohydrate-rich food, you may encounter problem with foaming. What you can do is you add few drops of pure oil to slow the foaming. For lipid-rich food, what you want to do is to heat sample until it catch on fire, but you have to be careful not to splatter the sample. To accelerate ashing, you may want to add pure glycerin as a fuel, or by adding oxidant, for example 30% peroxide solution. For alkaline ashing, you specifically need to analyze, you may use this if you want to specifically analyze chlorine or boron. Obviously, there are many modifications. to these otherwise very simple procedures. The point is you need to know what are you ashing for, what are the food metrics of your sample, and then know what are the necessary changes that can happen, and make the necessary changes in the method. Oftentimes this will involve lots of trial and error. So for previous methods, by dry ashing, you can actually weigh the sample after being combusted after incineration, and those weight will be equal to the total minerals, okay, in food. However, you may want to determine specific mineral content. This is sometimes important, okay, as presence of to know the concentration and types of specific mineral that is present in food. Okay, so good thing is that the major physical-chemical characteristic of minerals can be used to differentiate them from the surrounding matrix. Okay, one of them, few of these characteristics involve low volatility, the ability to react with specific chemical reagent to give these measurable changes, and also their unique electromagnetic spectra. Prior to performing this elemental mineral analysis, your food samples need to undergo ashing process first, okay, to remove mineral from the organic matrix. Okay, because mineral exists in traces amount, you have to ensure that your the sample that you use, okay, the water that you're going to use for these types of analysis, the reagent and glassware need to be very clean. Okay, they need to be free from contamination. So one way of how you can overcome this error is by using ultra pure water and to add blank for data normalization. So there are different methods that we can use, okay, to analyze mineral, but I'm going to focus specifically on this atomic spectroscopy. So now we're going to look at one of the traditional methods to determine, okay, the mineral content is by this atomic absorption spectroscopy. You can see here in this figure, okay, showing you the image of the instrument, okay, the flame atomic absorption spectroscopy, or AAS, and here is just an outline of how this instrument works. So what you have here, your sample is weighed and then dissolved, and then what happens is the solution containing your sample will spray it into the flame, and it will be then atomized. Okay, so now you have light from this radiation source, okay, of suitable wavelength will then shone through the flame, and some of this light is going to be absorbed by the atom of the sample. Okay, so now the amount of light absorbed is proportional to the concentration of the element. So for practical consideration, when you perform this AAS analysis, normally you have to make sure that a food sample is ash before you take this AAS measurement. So the resulting ash is dissolved in a suitable solvent, for example, water or diluted hydrochloric acid, okay, before you inject your sample into the instrument. Although it is possible to also analyze sample without ashing it first, this in particular very useful for vegetable oil, okay, where you dissolve it in acetone or ethanol and then inject them directly into the instrument. Because, as I mentioned before, the concentration of mineral elements in food are at the trace level, so it's very important to avoid any contamination by using very pure reagent when you prepare your sample for analysis. You also have to make sure that the glassware that you use is very clean and dry and contain no contaminating element. There shouldn't be any interfering substance in the sample, okay, whose presence would lead to erroneous result.